Okay, so I think we left off with, I was showing you how to do like means and medians and modes and variances and standard deviations in Excel, but we kind of also had a discussion about what the variance was. I think I had some like real easy, like 4 or 5 number data sets and kind of thinking about how we would go through and determine what the variance was of those. We'll just go through some more examples today. We actually will use the iClickers. Just realized I didn't start, but I'll start those when we get to that point. So
Is that free? I got an iClicker on that.
no, I think you have to pay. You might be able to do a trial run thing on. I'm not sure.
Yeah.
Talk to me after class, and I'll let you know. Yeah, if you ever forget your iClicker, talk to me after class. And usually, what I'll end up doing is kind of giving you whatever the base points were for the day, just none of the points for getting it correct. Yeah.
Verify that
You should be okay. When I upload these, if it doesn't upload, then you'll know there's an issue, but I can see kind of which ones, like it still records your response, even if you didn't register it. And once you register it, then it will sync up with your nick. And I don't have it pulled open, but if somebody with the app are wanting to get on there, I'll open it up here. So it should be able to see it once I get this one. I just always use AA. So even if it's even if I get people from other classes or something, it's pretty easy for me to throw them out. I don't really know why other professors make such a big deal about it. It's pretty easy to throw out anyone who's not in your class. So TikTok. All right, there we go. Throw this up here and we will dive into things. So let's say I had a data set that looks something like this. We talked about on Monday, and we're calculating the variance for a population. We're going to use this formula. So basically what we were doing was going through and for every observation, taking the value for the X variable we're interested in finding the variance of, subtract the mean of that variable, square that deviation or that difference, and then do that for every single observation. Once we've done that for every observation, add them all up, and then divide by the total number of observations we had. If it was sample data, we said it's the same process. We just divide by n-1, dividing by a smaller number kind of inflates that variance a little bit, kind of errs on the side of caution because we only have sample data. So let's say, oops, I have this data set, right? And I'm looking at it and I wonder what the variation is. So this is like Ball State football coaches. This is quite a few years back now, but the numbers don't really matter. The names don't really matter. So it's more about the principles. I keep using that. But it's also an interesting one that it kind of shows you like most of the salaries are kind of in a somewhat narrow range. And then you have an extremely large outlier for the head coach and kind of a lower outlier for the video tech guy, not getting a lot of love, right? So how would we kind of find the variance? Well, the first thing we need is what's the mean, right? Because that variance equation, we went through and found the deviation of each observation from the mean. So if I want to find the mean of this data set, hopefully it's not too bad, right? I would just do what? Add up all the salaries and divide by the number of observations I have here, which if I count these up, I think is 10. So we go through, add up every single salary, divide by 10, that gives us our mean, okay? So the mean kind of salary here is 134,000. You can kind of see like most of the observations aren't too far from that. We're going to have some that are really, really far from the mean, right? So another way of thinking about the variance, well, hold off on that. We'll kind of go through the kind of computation side, then I want to bring this something up. So if I wanted to find the population variance, what I'm going to do is I'm going to go through each coach's salary. I'm going to subtract this mean and then square that value. Once I do that for every single coach, I would then add all those up. And then finally, kind of similar to like the mean, I'll divide by n. I'm going to treat this like it's population data because it was every coach at Ball State in that year, right? Or football. So it's going to look like this, right? This looks like a lot, right? But there's another way we can break this down, I think, to make it a little bit easier when you're doing this on your own, right? So I took that head football coach's salary, subtracted the mean, squared that deviation. I took the next assistant coach's salary, subtracted the mean, squared that value. Did that all the way down to the video tech guy. And then instead of dividing by 10, we can also write this as multiplying by 1 over 10. I just did that because it would look goofy if I just had this big line over 3, and then over 10. It's really the same thing mathematically. right? Dividing by 10 or multiplying by 1 over 10. So another way of doing this, putting it the same value, is I'll start out with my original data set. I'm just going to build a column next to it, right? So for each one of these coaches, I'm going to take 489,000, right, representing thousands, subtract that mean of 134, square that value, and then write that number down. Then go to the next coach, 150 minus 134, squared, write that number down. Do that for every single coach, okay? Once I've done that for every single observation, add them all up. And then the final step was, well, I still have to divide by my total number of observations. So divide that by 10, I get that 14,700-ish. Any questions just about the procedure of how we would go ahead and calculate these variances? So here's where I want to focus on a little more is thinking about what the variance is and kind of the interpretation that we have. So if I think about, to go back a little bit, I might have already showed this to you, but it'll be helpful for the entire discussion. So if I was thinking about the mean, that was the equation I had, right? When we think about the mean, another term for it is the average. We're taking all of these numbers and then trying to figure out kind of where the middle of them are. But an extremely high value would have to be kind of offset by an extremely low value. It's going to get a number between, otherwise it's going to pull that mean up quite a bit, right? We talked about this with the skewness of distributions. So another way of thinking about this is, I'm going to just pretend for a second, we only have 4 observations. So there my n is 4. My formula for the mean looks something like this. But I can rewrite this and just pull that 1 over 4 out in front of each observation. All right, it's just something I can do mathematically. It's just a different way of visualizing. So what this is saying is that when I'm trying to find the middle value, I'm treating every single observation as though it's carrying the same amount of weight. Here, each observation is 1/4 of the entire data set. And so each observation is going to carry that amount of weight, 1/4, right? So they'll all influence the mean the exact same amount. And I'm finding the average number, the middle number. We're really doing the same thing with the variance, a very similar thing, in that, write this down real quick. Remember, I'm still dividing by n here. I guess I should have made sure this is use capital N. So all I'm doing here is saying, well, look, I'm no longer just adding up all the x values and dividing by n. I'm adding up all the deviations squared and dividing by n. So another way of kind of thinking about this, and I'll do like a 4 observation data set again. If I only had 4 observations, I could write out, and I'll move out of the way here in just a second. This is supposed to be x4. I'm running out of room, so hopefully you can visualize that, right? But I'm just writing it out for each of my 4 observations. But notice, I can pull that 1 over n, or 1 out of 4 in my example, out to the front, and each deviation squared is carrying the same amount of weight. So every single observation is going to provide you with a value that represents the variation in the data set. And then by dividing by n, it's almost like you're weighting every single deviation the same. So you're finding the average deviation from the mean squared, right? So before we're going to find the mean, we're finding the average value of this x variable. Now with the variance, we're finding the average deviation from that mean squared. Right, the average deviation from the middle part of the data. And some observations, right, like this head coach, 489,000, that's significantly above 134.5 or whatever the mean was found. So when I take that difference and square it, it's a really, really large value. It's going to add a really large value to that numerator because it is strong evidence that one observation shows us that there's a lot of variation in the data set. Now, for the other observations that are a little bit closer to that mean, when I subtract the mean and square that value, notice they're adding much, much smaller values to that numerator. because they're all observations, that there's much less variation in the data set, right? Because they're not very far from the mean. So once we do this for everyone, and we kind of do that divide by 10, it averages out. Notice, I mean, none of these observations here were as high as the variance we ultimately found. But that's because the variance, just like the mean, is greatly impacted by extreme outliers. Notice, yeah, all these are below 14,000, but that 125,000, the observation that gives us evidence of the most variation, is going to pull that variance up a lot. Okay. Does that kind of make sense? Any questions on that? We'll do a couple more examples. Okay. We'll skip this for now and probably come back to it. We have time at the end of class because I want to make sure we get through some of the stuff first. So let's say I had a question like this, right? I want to give you guys a little bit of time, probably 3 minutes or so, 3-4 minutes, to kind of try to calculate a variance on your own. That way we can kind of start to figure out where some difficulties might lie for you. You can ask questions after the fact, after we've all kind of worked on it. So let's say I have this commuting time data set, and let's say I tell you it's population data. So you're going to be calculating a population variance. I'll give you the mean. You don't have to calculate that. That was from last class. We had that was 45. So I'll give you a couple minutes. You can talk to the people around you, work on this, and try to come up with what the population variance would be for this data set. Okay? What symbol? Oh, like a centralized place? I'll put a formula sheet out when we get closer to the exam. But I would say for now, I think it's more of like just practice, it's just more seeing them and recognizing that this view is always going to represent the mean. Right? Yep. Yeah, so if you want to start practicing these, I'll mention things along the way. We're going to go through some stuff today that you can say you could do on your own. But that connect assignment's out there already as well. So you could start working on that and getting practice with some of these as well. Yeah. No, we'll keep going through. We'll go through a lot more examples, and even sometimes there'll be stuff in the slides I'll note like, we're not going to cover this, but here's like, I'll give you the final answer. So if you want to work on it, like if you're getting it right or not. Yeah.
I can go back and watch this.
Yeah. Like I said, we haven't done too much yet. We'll have more problems here, so I understand if it's still a little bit foreign. So remember, XI, it's just some notation we have that we're going to start out with the very first observation, and whatever the value of X is, we're going to take that. So this variable that we're interested in, X, for us, that's going to be the commute time. All right, so it's like going to that first observation, looking at that commute time, and then subtracting the mean, squaring that value.
Okay. So XI.
Yep, XI is just representing basically the X variable.
Make sure that we put these in there.
You mean order? So notice these aren't really ordered necessarily.
Oh, it's just the order you're given.
Yeah, you can just do it in the order. Just kind of a reminder, kind of walk through that coaching room, but you're going to want to go through for every observation. You're going to want to find the difference between that observation's value for the commute time and the mean, which you're told is 45. You'll then take that difference, square it, do that for every single observation, add them all up, and then for population variance, we should be dividing by what? Total number of observations, which here is 7. So give you guys about another minute or so to kind of work on this, and then we'll kind of go through it together.
So find the difference of the observation in the mean. Multiply that by 7.
Square that value.
Square that value.
Add them all up, and then divide by n, which here is 7. Yeah. Yep, just answer whichever of the one is. Yep, you just hit the button on your iClicker or on your mobile app. All right, we'll go for about another 15 seconds here, 4:45. All right, so if you haven't gotten an answer in, take your best guess looking at these and we'll kind of keep moving. So only 23 of us. All right, make sure you get it in. I'm not going to count because some people might have forgotten stuff. All right, 25. All right, we'll close it out now. Okay, so did anybody get the answer? Yeah. Yeah, it should be. I think I rounded it to the nearest integer here. It was 4 and 14 point something, right? So whenever I give you these, iClicker or even on the exam, I'm never going to try to trip you up with rounding. So I'm never going to give you like 414.1 or 414.2, or even give you 414 and 415. Right? I'm not going to make it so that just the rounding would lead you to get the wrong answer. So how did you come up with that? So kind of explain the process. And like I said, part of this is just getting used to like, you are going to have to kind of go through this and we're doing the in-class exam. You don't want it to take too long. So getting more experience doing these, being more comfortable with doing these types of problems is good. So I go through each observation. I would take that value for that X variable I'm interested in the commute time. So 20 minus the mean of 45 is negative 25. Square that value, write that number down. Next observation, take its X value 35, subtract the mean of 45, negative 10, square that value. It's 100, write that down. Go ahead and do that for every single observation. Then add all those deviations squared up, you get 2,900. We then said you divide by the total number of observations, or 7, and that's how you get that 415 for your population variance. Any questions or getting hung up anywhere where you have a question on it? Yeah. Yeah, if you want to, if you're able to think of it that way, then that's fine. I think for most people, like just remembering divide by that number is okay. But yeah, if you wanted to multiply by 1 over n or 1 over 7, that would have worked as well. Any other questions? Yeah.
What is the variance in comparison with the commute time? What is it?
So it is a measure of the variation that exists in the data, right? Like I said, probably I don't know if you'll find this in a textbook, but the best way to think about it is it's an average measure of the deviation from the middle part of your data set. And it's a little more than that in the sense that because we're squaring it, we're over penalizing being really far from the mean, but it is some measure of at least this deviation from the middle part of the data that we care about. Now, more practically, I don't want to waste too much time on this, but once we get further into the course, we'll start talking about things like z-scores and determining how likely or unlikely it is for us to see things. But the variance is where we have to start. I've already kind of mentioned last class, the standard deviation is really the exact same thing as the variance. We just take the square root, right? So that was just sigma, right? We take the square root of the variance, which is sigma squared. So you might have heard of things like 6 sigma. I don't know if we mentioned that in any of your classes, but it used to be kind of the industry standard. And we used to do things like, if you looked at the mean of a data set, I don't know, let's say the mean here was 100. And you had the distribution drawn out. What we end up always being able to say is that in this range, if I go 1 standard deviation below the mean, and then 1 standard deviation above, there will always be, I think if I'm remembering this number correctly, 68% of the data within that range. And then if I go 2 standard deviations out, I know there's always going to be, I believe 2 standard deviations is 95% or something, right? And so really the standard deviation tells us a little bit more, But really, we can't calculate the standard deviation without the actual statistic is actually the variance. We're just scaling the variance by taking the square root to get the more usable stat, which is the standard deviation. Does that help? So it's just telling you something about the variation in the data. Once we get to z-scores, we'll understand the standard deviation actually reflects something a little more. But to not overcomplicate where we're at right now, we'll kind of hold off on that discussion till we get to confidence intervals.
What kind of unit? Sorry, but what kind of
Yep.
unit is that 414?
So whatever the unit,
4.14%.
so think about whatever the unit of the variable you're working with is. It's almost like the variance. You can think about the units of the variance is going to be the same. So if it's commute time, it's minutes. If it's income, it's dollars, right? So think about it's kind of in the same units as whatever the variable you're measuring is. So here we had minutes. So it is a little bit abstract because it's like 414 what, but it's what's something else I can compare it to? Right, it's just a measure, and the measure, as long as our units are the same, we compare across data sets. That's what's important. It's like telling me it's 90 degrees out. Well, that doesn't really mean anything to me if I have no idea what 90 degrees feel like. If I'm not able to feel temperature, like you telling me a number, what does that mean? It just means it's hot. If this is high, it just means the variance is high. What does it actually mean? It's more of a useful number when you're saying, well, if it's 90 in this city, it's definitely going to feel more uncomfortable or warmer than it's 80 in another city, right? It's more about being able to kind of compare across these data sets. Like I said, once we get to standard deviations, it's a little bit more interpretable once we start using that for z-scores. But for now, just know that a higher variance means that the data set has more variation from that middle point, right? More so thinking about it as a comparison statistic right now. Any other questions? Yeah.
So would 414 be considered a number? Or would that be
So you really can't put a parameter on, like, no, you're not going to like this answer, but you can't really compare across different units with the variance. Because if you think about it, if I'm dealing with a variable like salary, I'm seeing way more variation just in the fact that salaries tend to be anywhere from 0 to over $100,000, right? And so when I'm thinking about deviations from the mean, it's way more likely to me for me to see a deviation of 10,000 from the mean if I'm dealing with the variable of income. But if I'm dealing with the variable of like height, right? Well, it's almost impossible for me to see a deviation from the mean of more than like 20 inches, or, so it's depending what the unit is, you're almost locking in that your variance is going to be within different ranges. And so we can't really use the variance to compare across variables with different units. It's really, we can only compare, like if I had different countries and I say calculate the variance in income for every single country, well, that's some measure. What would the variance be? So if I took income for a country and I calculate the variance, what's that somewhat capturing? What kind of political term? Income inequality, or right? So it'd be some measure of how much income inequality there is in that country's income. I could then compare that across countries because it's, as long as I put them all in the same dollar, same unit dollar, whether it's US dollar or whatever currency I choose, or I can compare the average, variation in height across countries or across states, right? But I have to be looking at that same variable that has the same units. Otherwise, you're right. There's no real context for what this actually is telling me. So like I said, for now, think of it as more of like a comparison statistic. Okay. So sometimes I don't think we'll get there till next week, but we'll talk about certain measures or statistics that we will calculate. And on their own, they have some issues and there's only so much we can do with them. And then later on, we usually start talking about other topics where they become usable for interpretation, which is like once we get to confidence intervals and hypothesis testing. But we'll see another example of that on Monday. All right. I also wanted to ask this question real quick. And let's see, I'll ask it real quick, and I'll probably just give everybody credit for this. I'm just kind of curious to see where we're all thinking at. So let's say I asked you to calculate this population variance. Which of these answers right away, so this is an IQ question, I want you to respond within like 15, 20 seconds, and then we'll talk about it. I'll give everyone credit, so just try to kind of, try to think about it a little bit. Which of these answers could you rule out right away as a potential variance just by looking at the numbers that exist in this data set? Okay. So which of these answers could you rule out just by looking at the numbers in this data set, all the different commute times? So think about that, 15, 20 seconds, and then I'll kind of close it out. Like I said, I'll kind of just give full credit for this one, no matter what you're answering. So I think we had 25 before. So make sure you get an answer in. I'm going to close it out. So we got 25. Okay. Yep, 26. Everybody sure you got an answer in? All right, I'm going to close it out. So which one can I rule out? It's kind of easy, but.
A.
Yeah, but why can we rule out A? That's a little bit
Because
harder.
the numbers are not all the same.
Yeah, I think we talked about it before. If I have a variance of 0, that literally means that every single observation would have been evidence that it wasn't any different than the mean. So when we took these it's the wrong one. We always skip these slides now. All these deviations squared would have to be 0. And the only way that's possible is if every single observation was exactly equal to the mean. Very clearly in our commute time data set, we have values that vary. Now, one of those observations was exactly equal to the mean, and so it did add kind of like a 0 into that numerator. Or it was an observation that was evidence that there's no variation in the data set. However, it was only 1 of 7, and the other 6 observations all provided evidence that there was some variation from that middle point, right? And so our kind of final kind of variance there ends up not being 0. Right? We can have one observation contribute 0, but we're never going to be looking at a data set where every single observation does. Okay. Any questions on this before we keep moving? Okay, so remember, the only difference between the population and sample variance formula was that I divide by n-1 instead of n. All right. So if I instead go, I told you to calculate the variance of this data set. I thought it was every employee. I thought it was population data, but in fact, it was only sample data, right? So I need you to go back through and calculate what the sample variance would be, right? So if you were to go back through and calculate that sample variance, recall that when we took all those deviations squared, they add up to 2,900. I haven't changed the data set at all. What would the sample variance of this data set be, right? So you don't have to go all the way back through and recalculate every deviation squared because we already know, oh, come on, that when we do that, those are going to add up to 2,900. There should be just one other thing that we do differently. I've already mentioned it, right, between a population and sample variance. So I'll give you about, I don't know, till where it says 1 minute to answer this question. It really shouldn't be too bad if we're understanding the concepts of how we're calculating this variance. Give you another 30 seconds. So nothing's changed, it's the same data. The only difference is you should have been using the sample variance equation instead of the population variance. If I told you that like, oh, I was wrong, it was actually sample data.
Yeah.
So it's exactly what we just did, right? And what did I say the only difference is? Instead of dividing by the number of observations, the sample was the one where we erred on the side of caution and only divided by n-1. Okay. Total number of observations. Yep. All right. If you haven't gotten an answer in, take your best guess here. I'll show you why this really shouldn't have taken very long at all. So we got 26. Thought we had 27 last time. All right. So why could I do this really quickly? And there's a reason why I kept going back and forth, right? I'm showing you what those deviations squared add up to. So what's the only thing I have to do different? Yeah, instead of divide by 7, divide by n-1, divide by a 6. Now, I didn't even have to pick up my calculator to know which one of these was the right answer. First of all, we've already talked about why 0 can't be the right answer. I know if that instead of a population variance, I'm doing a sample variance, I'm dividing by a different number, it shouldn't be the same thing that I just found. So I'm only between these two, but even more so, if I divide by n minus 1 instead of n, my denominator is going to be smaller. If I divide something by a smaller denominator, what happens to the fraction? It goes up. So I know that this new value that I'm calculating should be higher than what it was before. We know that it was 414 before. The only thing that's higher than that, of these four answers is 483. And really all it is changing that denominator. Okay? Any other questions on that before we keep moving? So we'll do this now. Where did I put mine? I left it over there. Okay, so a little bit about this idea of what the variance is, how we calculate it, kind of summarize what we've talked about with measures of central tendency and measures of dispersion. At least our kind of basic. Let's say I've got my first population, and they have a mean of 50. I calculate the variance. The variance is also 50. I got its distribution. Graphed out here, right? Now remember, when we draw out these frequency distributions, the frequency can be on our y-axis there. And so all these different values for x, right? We're saying these values are more frequent than these values, right? Because they're a little bit of the line is lower once we get up to these x values. So if I instead have another distribution, call it group 2, same mean. So if we're thinking about what this looks like, I'm just going to throw the means down here. It's kind of the middle part of my data. However, the second distribution has a higher variance. So having a higher variance tells me what about that second distribution? There is more, I'm going to put like saying words. Has a higher variance, that means the data set has more spread out, has more variation. In fact, thinking about it being more spread out is going to help you think about how to visualize the distributions. A higher variance means there's more variation in the data, it's more spread out. So when you look at its distribution relative to that first group's, the values near the mean are going to be less likely. While the values further away from the mean, when the data set has a higher variance, right, those have become more likely. So a higher variance really flattens out your distribution. Because a higher variance means it's more likely to see things that are further from the mean, less likely to see things that are right around it. Okay? The exact opposite is true if we go in the other direction. So I can use this up here to kind of show you that. Notice that if we go from the blue all the way down to the gray, they're kind of in order here. Right? We're going from let's go from a higher to a lower variance. So we'll start from gray and go to blue. Okay? As I start going to lower and lower variances or lower standard deviations, those are really synonymous, right? It's just we've scaled the variance to get the standard deviation. So a lower standard deviation is also evidence of being less spread out. So as we go to lower standard deviations or lower variances, right, these distributions now aren't becoming more flat, they're becoming more peaked. Another way to think about this is the variance influences kind of where your distribution is at on the y-axis, right? So as your variance or your standard deviation becomes smaller, you get this more peaked distribution, right? Or a higher distribution on the y-axis. As your variance becomes higher and higher, you get this flatter distribution or kind of lower on the y-axis. So that variance is related to kind of where that peak of your distribution is at on the y-axis. Okay? If I had two distributions but different means, so let's say I've got something like this. And I've got group 2. But the group 2 has a higher mean with the same variance. So I'll just draw out. Kind of where the middle part of that distribution's at. That's my first group, right? For 1 there. Having a higher mean, what's that going to do to this distribution? I'm trying to draw this out. Remember, like our X is kind of here. Yeah. Yeah. So it's actually all it's going to do, if it's got the same variance, it's going to be the exact same height and shape. It's just that the middle part of that distribution is a higher value, right? That mean for that second group was 100. So differences in means are just going to shift that distribution on the x-axis. Changes or differences in the variance are what causes it to be more or less peaked, right? Or higher or flatter, if you want to say it that way. Any questions on that? We kind of draw that kind of what we've been talking about with means and variances into what we were talking about with distributions. And then we're going to kind of go off on a slightly different tangent. Oh, I left it over here. So we looked at how we did this last class, if I remember right, like how we use these different functions. So we've already kind of went through this, but they're all in one place here. If that makes it a little bit easier for you once you start working on that first Excel assignment, which is up on Canvas. So that and the Connect were both due a week from Monday, last Monday, or sorry, 2 weeks from last Monday. So you've got some time to work on them. But I would kind of suggest start working on those early, get as much out of the way as you can so that you can come to me with questions and don't have to do that last second. Okay. I don't know if I really want to waste too much time on this. So I'll try to go through this relatively quickly. I'm not going to expect you to do anything with this. So it was more of something I just think is interesting. If we look at the variance, so we were kind of using the sample variance, we're using this equation. There's actually a second equation you can use. And if you're doing it by hand, it actually sometimes can be a little bit easier. So all we would do here is go through every observation, square each value, and then add them all up. So no deviations from the mean. And then subtract n times kind of that x bar squared. Right? So this will actually give you the exact same answer. It's just a different method of doing it. So I think I have the proof here. So I go back to that Ball State data. Basically, I instead would create a new column where I'm just doing each x value squared, add them all up, right? So if I add them all up, I get this 328,000. I could then take my mean, square it, plug in my mean squared. My n would be 10. I've got the sum of the x's squared now. The final thing is I would kind of divide by that n, right? I still need to divide by the total number of observations, and I would get the exact same value, right? That's exactly what we had found before. It was at 14,700. Now, I don't think this way is any easier, and it really doesn't highlight what the variance is actually capturing, kind of this average deviation from the mean. And so I don't start out with it, and I don't spend a lot of time on it. And I don't ask you to show me these steps or do this, right? But it is kind of interesting. There are multiple formulas for doing some of the things. Whoops. So I have here the mathematical proof. So like, how is this the same thing as this? I'm telling you that they give you the same answer. And I don't know, for those of you who have any interest or think that math can be cool, which I guess that is some subjective term. But if I start here, I can just pull that 1 over n minus 1 out, and I'll worry about kind of that later. I'll just deal with that summation. So I can kind of do this math, right? Xi minus x bar squared. I just get xi squared, xi times x bar, so on and so forth. Right? From there, if I have the math knowledge, I know that I can actually just distribute this summation sign if I'm adding and subtracting. So just distribute that summation sign. And I think I have a typo here. This should be what, xi and x bar. So I forgot the x bar. But here's where it gets kind of interesting. So anytime I have a constant, right, like X bar squared is just always going to be the same value no matter what observation I'm looking at, because X bar is just the mean. So if I do something like add up from 1 to 10, so the summation sign, and let's say add up the value of, I just have a value, 50. Well, that means I'm going to go add 50 up 10 times, or it's just whatever that n is times your constant. So when I do that summation of X bar squared, it's actually the same as just n times X bar. So I can do that. And then I kind of do this tricky thing where I multiply by 1, right? N over n is just 1. So if I multiply by 1, nothing changes, right? That's the same equation as I had before. Now I can start to do things like, well, if I have constants like X bar or n in my summation sign, I can pull those out front. So I'm going to pull my X bar values out in front of my summation sign. I'm going to pull my n out front as well, right? So I pulled my n and my X bar out. I'm left with the sum of the x's over n in there, which, what does this represent? If I add up all the x values, divide by the number of values I have, that's just mine. Should just be my mean, right? Add up all the x values, divide by the number of values added up. So this is actually just X bar. So this becomes n times X bar squared. 2 of these will cancel, and I'm left with what I said would give you the same answer as the original equation we started from. So, I mean, this is, I don't know. I think it's kind of interesting, like who the hell had the foresight to think about doing this ahead of time, like multiplying by 1. I use n over n. I don't know. I took some courses in college, like doing these proofs, and I always, I don't know. I think they're cool to see how they work. I understand, but I could never come up with mine on my own, right? So, you know, if you're ever interested, like, when I go through something like this, I'm never going to make you do this. I'm never going to make you like work through a proof or anything like that. I'm just showing you because it's somewhat interesting. And also, when I tell you something like, oh yeah, that equation is the same as that, well, I should at least back it up a little bit, right? You shouldn't believe everything I say if I can't prove it. So, different way of doing the same thing. We've already talked through all of this. The thing that we're going to end today on is weighted means, right? We might touch on weighted variances a little bit. And I think it's already up on YouTube. You might have seen it before class, hopefully it didn't freak out. I put up like a 3-minute video that was meant for one of my other sections that meets on Friday. I gave them a pre-class video before class on Friday. For you guys, I'll end up posting a video tomorrow that I'll have expected you watch before we meet in class on Monday. Right, and I might start Monday's class off with some iCareer questions about it, right? Or Wednesday. Sorry, you're right, Labor Day. Or next class, right? I'll expect you to watch it. So for them though, they have class Friday, so I gave them a small one to watch before class Friday. And I figured because I already have it recorded, I just put it up on our page. If you ever want to go back and kind of review just weighted means, it's kind of a nice little like introductory example. Okay. So with that being said, we're going to dive into it for the first time. So up to this point, we've been lucky enough to have data where we can see it at like the individual level, right? Or each observation kind of should be treated the same, right? In, you know, every individual carries the same amount of weight. But what if we had group data, right? So I already kind of mentioned when we're thinking about the mean, we kind of rewrite it. And if I keep it more general, not just 4 observations, we said it would look something, start using 4 after I said 4. Right? Gosh, bless it. It would look something like this, right? We would just have every single observation's value multiplied by 1 over n. I just rewrote my mean equation a little bit so that I'm thinking about, okay, every observation is carrying the same weight in this mean. The problem is a lot of times we're giving group data, right? So sometimes data might be presented to us like this. And this is, I think this is the example I used in the video, but I really like it. I could change it though to make it a little more interesting. So let's say. Actually, got an example. For so let's do engineering. Let's do pharmacy. We'll do my sister. Psychology. I'll just keep those three. So let's say I'm kind of looking at the starting salaries, right? For three of my main majors, if I'm a college or something like that. Right? So when I went to Purdue, right, engineering's big, pharmacy big, is big. I chose anthropology to choose some other kind of program. So you can think about maybe, I don't know, got 65,000. I don't know how much pharmacists make. We'll say it's quite a bit. And then here, quite a bit lower. Right? Might be being generous. So I'm not trying to. It's just reality. So I'm not trying to. So we got our starting salaries. We wouldn't want to just say, okay, what's the average starting salary of someone who leaves this college, right? So we look at these three majors, we add them up, divide by 3. That's the starting salary, right? Well, not if you're a school like Purdue, where half their damn students seem like they're engineering, right? Engineering program. So we would need to also know, like, well, no, this is the average starting salary of these majors. How many students does this represent? So maybe, you know, if you were looking at a sample, we don't have every single person in the university, but if we're looking at a sample, and maybe this was represented 60 students, this represented 30, but this only represented 10, right? So if I ignore that and I just add them up and divide by 3, each one of these is going to be carrying an equal weight. However, I can see that there's way more students, this salary represents way more students than this salary does. So I need to somehow use these number of students as some type of a weight so that I make sure that starting salary of the engineering majors kind of influences my mean a little bit more than the anthropology major kind of average starting salary. Now, this is only a problem if we have the data presented or only have group data. If I could see every individual student's starting salary, well, then I could just add them up, divide by the number of students I have. But I can't see that, right? I've got like this data grouped. Okay? So I used to use this data of fast food sales. You can just ignore this. I kind of like the one I just did now a lot better. That's why I did it. But if we have this group data, I'm going to have to use this formula, right? So all this formula says is go through every observation. And when we have group data, the number of observations is going to be small, right? I only have 3 over here. So go through every observation, take some weight, and usually that's going to be some type of like a frequency, or here's the number of students that have that major. Multiply that weight by the value, the value for the X variable you're interested in. Do that for every single group, right? Every observation here. Add them all up, and then divide by the sum of the weights. So what that's going to look like for this data set will be something like this. I'll go through my first observation, multiply its weight, right? I've got 60 engineering majors by the average starting salary for engineering majors. So then add to that the next observation, take its weight, it's 30 students, multiply by the average starting salary for those pharmacy majors. Take the weight for anthropology majors, there's 10 of those, times their average starting salary. That's my numerator. The sum of each group or each observation's weight multiplied by its value for the variable I'm interested in, X, which here is starting salary. I'm then going to divide by the sum of my weights. Well, the weights I was using was just the number of students I had to each major. Good. Yeah. So to add those weights up, right? 60 plus 30 plus 10. Okay. Any questions on that? Yeah.
So do you have to put parentheses like that, or is it like that?
If I was putting this into my calculator, I would just have to do that. And then do this ahead of time or put parentheses around it. Right, so if I do this, then hit divide by 60, I'll do that first, right? I need to make sure I'm dividing by 60 plus 30 plus 10. Questions on that?
Can you add the bottom first and then you said the back bottom?
Probably easy that way, right? No, I'm just writing this out to be like mathematically, like show you everything. Yeah, for sure. What I would do if I was doing it, calculate this, write the number down, figure this out, write the number down, then you have one number divided by another number, right? You don't have to put this all in your calculator at one time. Well, we're okay with kind of this process for now. We've got some more examples. But I wanted to show you a slightly different way of thinking about it. I hate this classroom because I don't have a lot of board space, but we'll keep this up here. I'm going to be referencing this, but I'm going to be doing the work over here, and then we can kind of make the connection hopefully. So it's probably easiest to calculate your weighted mean the way I just showed you, but there's another way of thinking about it. And so there's certain examples where I think this is really just going to make it hit home a little bit more. So the first starting salary I had was what? Was it 65,000 over there? And if I look at how many students was that 65,000 representing, it's representing 60 students. 60 out of 100. So I don't know if you've done like expected values in other classes, but a lot of times you can use things like, well, what's the probability something occurs? Well, here we can use a similar idea with, I need to be weighting this value by whatever the proportion of the data is that group. So instead of the other way, I could say, well, I know that 65,000 represents 60 out of the 100 students in my data over there. Now, I can't observe every 100 students individually, but I know that those numbers are reflecting 100 different students' salaries total, right? I could then add to that the pharmacy major's starting salary, and they made up the proportion of 30 out of 100. And then I could do the anthropology majors, they were 10 out of 100. And now if I compute this, it's going to give me the exact same answer as if I did it over this, did it the method that I had showed you over there on the left-hand side of the board. Right? We're really just thinking about it a little bit differently. And if I wanted to, you're kind of reminding me of this saying, well, isn't the denominator just 100? Well, yeah, this is just 100. So if instead I just had 100 written here, and I pull it out, everything's being divided by 100. Notice I have 60 over 100 times 65,000, 30 over 100 times 70,000, 10 over 100 times 40,000. Here's basically what I have written over there, right? So just two different ways of thinking about what the weighted mean is telling us. Either method, what they're really doing is it's taking each one of these values and it's weighting them appropriately, right? Whatever fraction of the total that number represents, we're going to weight it by that much. One more thing here. So if instead of like using the number of students, I want to think about this as like my weights are like the fraction of students coming from each one of these groups. Technically, I'm doing the same equation. So here my weights are going to be these proportions, right? But if I'm using the proportions as my weights, I basically have my numerator right here. But then if these are my weights, what do those weights add up to? 60 over 100 plus 30 over 100 plus 10 over 100, right? I'm just adding up my weights and putting my denominator in there. Well, if I've kind of taken the frequencies and made my weights proportions already, right? I divided each one of those frequencies by my total number. What will these add up to? 100 over 100, which is 1. So my denominator, if I use proportions as my weights, will always be 1, which dividing anything by 1 doesn't change anything, right? So we don't really have to worry about the denominator if our weights are proportions. Okay. More often than not, they're given the proportions, we're usually given something more like that with frequencies. And whichever way is going to be easier for you to think about, I would say kind of go with that one, or whatever makes the connection kind of easy. Okay. Any questions on this weighted mean? I got another example we can kind of work through. Okay. So steps to calculating a weighted mean. So I just kind of have it written out, right? You'll go through each observation, multiply that group's value for the X variable we're interested in by its weight. Usually that's some type of a frequency. Add those all up. Then third step, add up all your weights. So you have the sum of your weights. And then, like I said, if you break it up into these steps, now you just have a value for your numerator, a value for your denominator. What goes in, we'll be done. Okay. So I have another example where I went out and grabbed a bunch of data from the census. So I've got kind of the average income, but they don't let you see it for every individual they have in this huge sample that they have. They can only show you based off of certain demographics or regions of the country. So I pulled these out and basically I've got this variable X, which is income, but I can only see what the average, kind of combination of gender and race for each one of these combinations of gender and race, right? So I've got it for males, I've got it for females, but each one of these average incomes is representing wildly different amounts of individuals, right? If you look at the demographics of the US, there's certain racial categories, at least the way the census classifies it, that are going to make up a higher or larger percent of the overall population, right? So anytime we have these average incomes, if we want to find the average income for everyone across the entire United States, we're going to have a little bit more work to do, right? Because we can't simply add these up and divide by 4, because each one of these represents a very different number of people. Okay? So if I wanted to find the overall mean income for men here, right, I would actually have to find a weighted mean, because I've grouped data. Can't see the individual incomes. So what would I go through and do? Well, I'll take each group's X value, right, or the income value here of 59,000. My weights are going to be the number of people in that group from this original sample data that I can't see. I only get to see the group data. There's some original sample data that did exist with individual level income, right? But I'm only seeing the group data. So 59,000 times the number of people in that category, or the number of white males here, so 73,000. Write that number down. Go to the next racial group, 38,000 average income times almost 12,000 people, right? Add to that, next group, 60,000 times 6, so on and so forth. Once I add all those up, right, that's going to be my numerator, the sum of all those products. Now here I kind of made it easier. I already showed you what the sum of the weights is, right? So here are my weights. If I add all those weights up, I get that 108,000. Okay. So what that would look like is something like this, right? I just go through for each group, take its weight, multiply it by its X value. Once I do that for all 4 race groups I have here, I add them all up, divide by the sum of my weights, which I wrote this out here. I could have done it ahead of time, kind of like the previous example. Right? Now notice, I've got some like lower income values here, but they're from groups that are relatively quite a bit smaller in my sample than kind of the white male category. So the value that's going to have the most influence over this weighted mean is going to be whatever group is the largest. So this 59,000 is going to have the largest influence over what our weighted mean is, which makes sense, right? If that number is reflecting a higher number of people, it should be carrying more weight, right? Questions on this example? So I don't know what you would get if you added these up and divided by 4. My guess is you would get something that's less than 53,000, because it would then be treating this value the same equally as these two values, when in fact, looking at kind of the relative size, it's quite a bit larger. Right? And we could do the same thing for female income here. So on the slides, there's white boxes here. You can just pull them and move them. And if you want to, this would be a good one to like work through on your own and try to be able to reproduce this number, right? Try to find kind of the weighted mean for female salary from this data and kind of make sure that you're comfortable working through a problem like this. Okay. I'm not going to go through it explicitly, but it's like, things, if you're looking for things to do to make sure you're kind of keeping up to date on the content. We could also do this for regions, right? So if you're listening to me at all, Hopefully this is a really easy eye clicker question. We'll see how much you guys are kind of following along and paying attention. But if I were to ask you, and I think I maybe supposed to have a slide, Northeast would be A, Midwest B, South C, and West D, right? So A, B, C, D. Which of those regions, kind of A through D, kind of following them in the order written, would have the most influence over the mean, right? Whether or not I'm calculating the average male income or average female income, which of these is going to have the most influence over that mean? It shouldn't be, there's no computation. Yep, so just A, B, C, D. I'll probably go to the next slide and it'll be the one that I put them on. All right. Take your best guess to close it out here. So 27 should be one more person. All right, let me close it out. So what region of the country here should carry the most weight when we're calculating our weighted mean? The South, right? Oh, of course I did have it there. So, right, the South has significantly higher number of people in that category. So the value that we see for the average income in the South is representative of almost twice as many people as some of these different regions, right? So it should be carrying the most weight, right? And that makes sense, right? It's representing more people, okay? Similar to when I said, right, the white male category was going to carry a little bit more weight because it had the highest number of people. It represented the highest number of people. What do I want to do here? We do variance. We got 10 minutes about weighted variance. I want to do some statistics. All right. What if, just thinking about these things, let's say I had this data. Yeah.
You do this on Excel, you can call, you do this on Excel, or is it-
I can show you how to, actually, it's a good idea. Instead of going into variance today, I'll actually show you kind of how to do this in Excel, but I want to hit one more thing first. What if I was going to try to calculate the average income across both regions and gender here? How could I use this data to do that? It would actually not too much more complicated. So now I don't just want average male income and average female. I want just average human income, right? In the US. So it'll be very similar to what I was doing before, right? I have two different kind of columns, but really what I could think about is now that I'm not trying to find like gender specific income. I could just move this data down here, have two columns. Here's my X variable, here's my weights. And then it's the same process. So I would just go through, take the Northeast number of individuals, multiply by their income, Midwest times their income, plus the South times that, plus this, times that, plus this weight times that X value, plus this weight times that X value, right? And now I'm just adding all those up. And then when I divide by the sum of my weights, well, now I've got like 8 different groups, right? I've got men in the Northeast, I've got women in the Northeast, I've got men in the Midwest, I got women in the Midwest. So I have 8 different weights. Put those some of those weights, I can just add those up like that. So how would I do this in Excel? Excel makes this actually quite a bit easier. So I'll show you how we could do this. And I'm sure there might even be, we'll kind of play around. We'll see. So I'm just going to copy this and paste this into Excel. Kind of show you how we could use Excel to. If I can get it. There we go. All right, there we go. So I'm just gonna. Nope. See, we make sure we can see all this. Also, if you're not real familiar with Excel, if you do end up with a column that's like too narrow, you won't be able to see the numbers. It'll just show you a bunch of pound signs. If you just left click in between the two columns, you drag it over so that it's wider, you then should be able to see the values. And I'm going to change this so that everything's kind of looking the same. All right. Well, now there's no line in between there. All right, go here. There you go. So if I had the data that looked like this, and I think I lost like that this was female and this was male. The easiest way to do kind of just find the male weighted mean, right, is create a separate column, right? So I would do something like take my weight, multiply it by the X value. So I'm just going to do that for each group. Let me zoom in here because I just realized it's pretty hard to see. So all I did there was take the weight for that group, multiply it by that group's value for the X variable. If I create this column right next to the data, notice when I copy this down, it updates my cell references, so just keep doing it for the next region. Right? So I now have everything I need for my numerator. Right? So here I just need to take the sum of those products. So in Excel, we have that sum function, parentheses, just select what we want to add up. And now I get my numerator. The other thing I need is what? The sum of my weights. Nope, don't autofill for me. The sum of my weights. Well, that I can just use the sum function and add the weights up over here. Right? Now I've basically got my numerator. Let's see if I can spell that without. So, and my denominator. So now when I want my weighted mean, it's going to take, what's an H7? So just take that numerator divided by my denominator, I'm done. Any questions? I did it kind of quick. I'm going to see any of that again. Yeah. I was going to say, so that's the thing I'm not 100% sure on. Let's see. Do W, if I do there. I can almost guarantee you that there is. Not variance. We just want a weighted average. It looks like there may not be actually. Yep, so it looks like for whatever reason, no one has programmed that into Excel. It's really not that difficult. I mean, to break it up and do it like this. Now, one thing I also want to show you is you don't have to break things up in Excel like into separate cells like I did here. If you really wanted to, you can use Excel just like a calculator, right? I could have said, okay, take the sum of all the weights times the X values and divided that by the sum of my weights. So I can put it all in one cell. It's just a little bit easier if I break it out into parts. It also helps that I break it out into parts to identify places where I might have made a mistake, right? But you can you can put multiple functions in the same cell. You can put multiple functions and also have some mathematical operators like divide them, right? So I guess the way to think about these functions too is if we're trying to throw them into like where do they fall in order of operations, they'd be like above the parentheses, right? Like whatever is inside of this sum function, that's the first thing that's done, right? It does whatever is in those functions first, and then it would kind of follow your traditional kind of order of operations, okay? Let me see. Thought maybe there was an average of. Yeah, I'm really surprised that there isn't a weighted variance. I usually don't go too much into the weighted variance in Excel, so I wasn't sure. But that is surprising. Any questions about kind of doing this weighted mean? So on Wednesday, we'll finish and we'll do some weighted variance and another example that looks a little bit different, but it's basically still weighted mean, weighted variance. We'll then dive into kind of the next subject, which is probably, that'll be kind of what the video is about. That will be the next topic that we're going to jump into. And like I said, I'll get it up at some point tomorrow, and then just expect that you've gotten the YouTube. It'll be 3-4 minutes long. Just watch it prior to class on Wednesday, and I'll probably have a couple questions that are related to that video in class. Okay, just saves us a little bit of discussion. We're losing a whole day next week, so we've got to kind of catch up with the other section. So that'll help us do that. Okay. Any other questions from me before you guys get out of here for today? Okay, start working on that Connect and that Excel assignment. Feel free to reach out to me if you have any questions, or if you want to stop by my office, you can always send me an email if my office hours don't work for you. And so, one thing I didn't mention, I also don't mind doing Zoom office hours if you don't want to come to campus. So,
Hello.
hey, let me stop this real quick.